Welcome to the lecture on mechanics in spinning process. So, in this lecture today, I will talk about the mechanics behind cyclic aggregation, inside the rotor spinning technology. Because of cyclic aggregation, we get the back doubling. Now, many of you may be understanding what is back doubling is, but how exactly it forms, what is the mechanics behind that, that is what we will see today. Now, before going into the details, if you look at the rotor spinning, it is very simple. We feed the sliver, the feed roller feeds it to the opening roller, which opens the fibers. Some of the trace materials are going to be ejected, and the fibers are going to be taken by the fiber transport channel and delivered to the rotor. In the fiber transport channel, there is going to be some draft also, because the area of cross section of the transport channel gradually reduces. So, there is going to be draft. Now, this drafted material, which is well opened almost to individual fiber state. So, these fibers are going to be deposited inside the rotor. Then a seed yarn is going to be introduced from the center of the rotor. As we pull the seed yarn, the yarn formation going to continue, and it will be continuous after that. Now, what is happening inside the rotor as the material is delivered, as the fibers are delivered inside the rotor, that is what is very important, and we will talk about that in this lecture today. Now, the rotor yarns, they are formed from the fibers that are getting collected inside the rotor, like I said in the last slide. Now, this could be the individual or small group of fibers that are being deposited onto the rotor wall, and because of the centrifugal force, the fibers move to the groove, rotor groove, and in the process, as the seed yarn is introduced and as the seed yarn rotates, the twist is going to be introduced and the yarn is going to be withdrawn. Now, in order to gain full understanding of what is happening and how the rotor yarn structure is developed, we need to understand, we need to put little bit more time on how these fibers are getting layered in the rotor groove in order to form the ribbon of fibers, which we call it as cyclic aggregation, right. And the insertion of twist inside this ribbon and delivering it, that is going to withdraw the yarn continuously. Now, if you look at it, the doffing tube is there in the middle. This gives the top view, for example, of the rotor. The fibers are collecting at the rotor groove, which is on the edges, and as we pull the yarn through the doffing tube, the fibers that are collected on the circumference, on the edges or the grooves of the rotor, they are going to be peeled off from the point P, which is shown here. That point is called as the peel off point. The P point, which is shown there on the circumference of the rotor, that is the peel off point. Now, since the ribbon which we are pulling it at the delivery rate, which is equal to, say, let us say V sub d, right. So, the yarn is going to be delivered at the speed of V sub d. Now, this peel off point is going to rotate as we pull the ribbon and peel off happens, right. So, the peel off point P, it is going to rotate around the circumference of the rotor. Now, what will be the speed of that rotation? That will be equal to V sub d divided by pi d r, because V sub d is the delivery rate and it has to make one rotation, that is it has to cover a distance of pi d r. So, how many pi d r's it is going to cover in V sub d? That is going to be given by V sub d divided by pi d r. So, it has to rotate around the circumference of the rotor in order to get peeled off and material getting delivered to. Now, that means relative to the doffing tube, the peel off point, it has to rotate much faster, right. It has to rotate faster than the rotor itself. The rotor is making certain number of rotations and the peel off point has to move faster than the rotor, then only the peel off happens, right. So, if you say that n sub p is the peel off point rotational rate, that is going to be sum of two things. One is the rotational rate of the rotor itself, that is given as n sub r, plus in addition to that the peel off point makes additional rotations as explained earlier, that is v sub d divided by pi times dr, where the dr is the diameter of the rotor. Okay. So, you can also imagine, suppose if you stop the rotor, you do not rotate the rotor, that means you make n sub r as 0, then the peel off point will go around the circumference of the rotor at a speed of v sub d divided by pi dr. So, then you start rotating the rotor speed adds to that. So, that means the peel off point speed is going to be sum of the rotor speed plus v sub d divided by pi dr. Now, this high speed camera image, it clearly shows what is happening at the rotor wall. Now, the peel off point is shown here. The rotating arm of the yarn, it meets the fibers which are collected at the rotor groove. Now, in this case, it is very clear the twist is flowing only up to the peel off point. Let us say peel off point is the one where the arm and the fibers are collected on the rotor groove meet. Now, this peel off point and the twist flow point, it can be exactly same, or by changing the doffing tube profile, that is by changing the torque provided, by changing the profile of the doffing tube, it can be made such that the twist can flow even into the collection of fibers, that is into the rotor groove also. So, at the startup of the spinning, what one does is we just simply feed the sliver, the fibers are getting collected in the groove, rotor groove. Then we introduce the seed yarn. So, by the time we do not have any control over the amount of fibers that have already collected. So, the count of the material which is collected or which is peeled off in the beginning need not be equal to the count of the yarn. So, the required count, it can be obtained only after we remove the initially deposited first ring of fibers. So, after till that we do not have any say on the what is the count of the yarn that is coming out, right. But once we remove that, after that whatever material which is delivered to the groove, that amount of material is going to be delivered out of the rotor also. That is steady state is going to be reached only after the removal of the first ring of fibers, right. After that we can really say, okay, this is going to be the count of my yarn. Now, let us take this picture here. So, here the rotor is shown as the circle and the fiber feed point F, so that is the feed channel which is coming over there. Then you have the seed yarn tail which is shown there, and also the point P, it denotes the peel off point, and there is a point A also shown over there. So, this point A is a fixed, let us say it is marked fixed on the rotor. So, as the rotor rotates, this point A also moves along with that. There is no relative speed between A and the rotor, whereas the point P is a peel off point, it is going to move forward depending upon the take up rate V sub d. So, there will be some relative speed between P and A, relative displacement, relative speed also is going to be there, whereas the fiber duct that shown as F, it is stationary, it does not move with the rotor. So, the fiber is going to be delivered right at that point. Okay. Now, let us see what is going to happen as the rotor rotates. The rotor, let us say it is going to rotate in the counterclockwise direction. Okay. So, the point A is there, P is there, F, all of them are at a single point to start with. Now, for the sake of simplicity, let us ignore the effect of twist contraction. So, length of the yarn does not change as we twist. Then again, like shown in this drawing, at the instant of the seed yarn touches the fiber assembly in the groove of the rotor, all these points P, A and F all are at a same place. Okay. Now, from the F, the fiber is going to be delivered onto the rotor wall, and then because of centrifugal force it will move to the grooves. That distance is very less. So, let us assume that is insignificant. So, if we do that, then A, P and the delivery point of the fibers all are at some place. Then again we assume that the doffing tube novel, like I said earlier, is very smooth. That means, the amount of twisting torque that is provided is just sufficient, so that the twist flows only up to the point P. Now, in contrary to that, suppose if we put a navel which has a groove in it, then it will provide higher twisting torque. So, because of that, the twist will further flow into the fibers which are collected on the groove, right. So, in order to avoid that, we assume that smooth doffing tube novel is used in this case. Then the fibers leave the exit of the transport channel, they are going to be deposited onto the rotor wall, they slide down and then move to the rotor groove. So, these are all some assumptions that we make, so that we can proceed further to understand how this cyclic aggregation happens. Okay. Now, having assumed these parameters, now we think that the rotor is going to rotate in the counterclockwise direction, right. So, as it start rotating, the peel off point is going to move with slightly higher speed than the point A, and it is going to create small gap between P and A, right. So, A is the point which is a fixed mark on the rotor, it does not move with respect to relative to the rotor, whereas P is going to be moving forward, right. In that process, it is going to collect the ribbon of fibers, and as we pull the yarn, right, or as the winding happens, the yarn is going to be pulled, right, and the twist is going to be introduced into the tail of the yarn, right. Then as the rotation continues, say the rotor is moving from position 1 to 2, right, 1 to 2, then P is going to be moving faster than the point A, right. So, that will introduce that gap between P and A, which is shown as y here, right. So, this y is going to be equal to the delivery rate, right. How much yarn is pulled out, that much gap is going to be created over there, because the yarn is taken out. So, as the equation which we have seen already, N P is equal to N r plus V sub d divided by pi d r indicates, this makes N P is going to be greater than N sub r. So, as the rotor is moving in the counterclockwise direction, right, the fibers leaving the transport channel are going to be entering into the groove. So, they will be depositing the fibers on the top of the already existing layer, which is shown here, right. So, after the gap, the fibers will be deposited starting from the point when it leaves the location 1, because the fiber deposition happens always irrespective of the rotation of the rotor. The deposition is going to be happening at point 1 only. So, as the rotor rotates counterclockwise, the new fibers are going to be deposited in this area here. So, rotor is going to be rotating like this. So, new fibers are going to be going, it will be following the peel off point, and this gap between peel off point and A, it is going to gradually increase as the rotor moves towards 2. So, the gap y, that is going to be simply proportional to your V sub d, delivery rate. So, y will be equal to t times V sub d. If it is t minutes have taken for the point A to reach point 2, then the gap, by the time the rotor has reached the point 2, then the gap would be, the length of the gap y will be t times V sub d. So, that means as it reaches the point 2, what is going to happen? The new layer also would have been formed behind the peel off point. So, 1 to 2 is a quarter of a rotation. So, that means nearly quarter of a rotation length or circumferential length equal to quarter of the circle, that much new fibers would have been deposited onto the already existing ribbon, right. So, then again similarly, as A moves from 2 to 3 and 3 to 4 and all that, this gap is going to be widening, okay, because P is moving much faster than A, right. So, accordingly 1/4 or half or 3/4 of the new material would be deposited. Now, what is going to happen is, as the point peel off point, correct, it makes the rotation, and one full rotation, if it comes back to the point 1, right, where it started. Okay. So, at that time this gap y will reach a maximum, that we call it as y max, right. So, y max is obtained once the point P makes one full rotation. Till that time it is gradually increasing, right. So, once it reaches the point 1, this distance gets maximized, and after that the new fiber is going to cover that gap, that we will come back in the next slide also. Now, at this point we can write this y max is going to be how much? It is the distance that is covered, or the amount of material that is delivered when the peel off point makes one rotation. So, time for one rotation is going to be 1 over n p. So, 1 over n p multiplied by V sub d, that is going to be the length for y max, correct, because the y max reaches on one complete rotation of the peel off point. For that it takes a 1 over n p time, and it is moving at the rate of V sub d. So, it is V sub d divided by n p, correct. So, we see here that y has reached the maximum here, and at the same time it has reached the point 1, and also the fiber delivery point also right there. Now, further movement of P will lead to what? The fibers are going to be delivered onto P, and in the gap following P between P and A. So, that means this gap is going to be filled up. Okay. So, the ribbon continues to be peeled off from the groove and twisted into the yarn, and new gap begins to cross over the newly deposited fiber layer at P, and following the gap is going to be also filled, right. So, y max is going to be filled by a new layer, a second layer is going to start at this point. So, the second layer will be right behind, just behind the point P, and it will say, for example, if you have to imagine, so if you see this is the rotor. So, here the yarn arm is going to be here. So, the fiber is being delivered here. So, the P and for example, your point A are here, right. So, you have a layer of fibers. Now, this gap has been there after one rotation of P. So, as it moves forward, okay, now these fibers are being delivered continuously. Okay. So, this gap is going to be filled by this newly fed fiber, and then it will as it moves still further. Okay. So, you have a new layer here followed by old layer. So, as it continues rotating, you will have a single layer of new fibers, followed by that single layer being deposited onto the already existing layer of fibers. Okay. So, again as the rotor is continuing its rotation like here, and the arm is going to be rotating much faster than that, little faster than that. So, your gap is going to be created again, new gap is going to be created. So, the whatever gap that was created in the first rotation, it gets filled up, right, and again as the second rotation starts, new gap is going to be created. Okay. And again the same process is going to continue, the gap will keep on be increasing, it reaches y max when the the point P and A are at the starting position. Then after that a new layer again is going to be formed, right. So, for that the first time you have one layer, then second time, so you have one layer which is formed, then you have the new one will be starting just above that. Okay. And as the rotor is rotating, this will keep depositing on it. So, layer by layer it will continue like this, right, and that is why it is called as a cyclic aggregation process. So, you have a tapering kind of thing, right. Once the originally which were the fibers which were there on the rotor, right, all of them are peeled off, then you have the newly deposited fibers which are available. Okay. Now, these newly deposited fibers will be number of layers will be such that at the peel off point you will have enough number of layers which will constitute for the count of the yarn. Following that you will have a taper. Okay. So, you will have a layer which is ending here, the one layer is ending here, the next one ending here, third one like this. So, like this you will have a tapering effect, and since it is the ribbon is formed by deposition of different number of layers, right, we get a doubling effect. That is why we call it as a back doubling. We all know that whenever we go for doubling, there is going to be improvement in the mass variation. So, this back doubling which is obtained because of cyclic aggregation is responsible for more uniform yarn that is produced in the rotor system. Okay. So, what is going to be the back doubling? How much will be the number of layers that will be formed? How do we get it? So, for that the peel off point, okay, if it covers one complete circumference, that is when cycle is going to be completed, right. So, for example, the peel off point started from here, after one rotation it has come here and the gap is there like that. So, if it covers one complete circumference of the rotor, that is the completion of one cycle. So, that is given by the the time Tr. Tr is given pi dr divided by Vd, that is like for one complete rotation of the peel off point around the circumference, how much time that it takes, right. So, during that time your number of layers that is formed can be written like this. Tr is the complete time taken for the peel off point to make one rotation times the number of rotations of the arm that is moving, right. For every time it is for every rotation of the arm there one layer is formed, right. So, to Tr times the Np, that is going to give the number of layers, total layers that are formed in one cycle. This also is equal to pi dr divided by y max. Now, why y max? Because for every rotation the peel off point is going to be ahead by y max. So, when it makes one complete rotation, it is going to be like pi dr is the circumference of it, and how many y max are there? Pi dr divided by y max, that is going to give the number of layers that are deposited, that is one and same. So, right. So, NL is going to be TR times NP, that is also equal to pi dr divided by Y max. So, that is going to be the number of layers that are formed to make the yarn. If you have so many number of layers, you should be able to reach the count of the yarn. So, all other parameters like the number of fibers in one layer, the fineness of each fiber, right, all of them should be suitably selected. So, that your number of layers NL times XF, which is the number of fibers, and TF, which is the decitex of the fineness of the fiber, that should give you total linear density, that is equal to yarn count in text, right. 10 to the power of minus 1 is given here to adjust for the units. So, basically the number of layers that you form, that is going to be important, and the number of fibers in each layer, that is going to be again another important parameter, and fineness of the fiber. These three put together will give the required count, it should give the required count. Now, in this one, if you can reduce the number of fibers in each layer and increase the number of layers, as you increase the number of layers, number of doubling, your yarn property is going to be improved still further. For that, we have to reach very fine opening and high amount of drafting, so that least number of fibers are delivered for each layer onto the rotor from the fiber transport channel, right. So, the thickness of the newly formed ribbon, right, like I said, it reaches to the required thickness over here by combining so many number of layers. Then after that, it is going to be tapering down, right, and as the process, it is a continuous process. So, a new gap is going to be produced, and then this material is going to be coming out, right. Now, if you get some idea about this gap that is available, Y max, let us say, then that will give a better idea about the yarn structure that we are getting from the rotor spinning. Now, for that, what is the Y max that we have written? It is equal to V sub d divided by NP. Now, if we take typical example of the values that are used in the rotor spinning, let us see how much will be the gap length approximately. Say for example, if you take, it should come in the order of few millimeters, we can see that. Say for example, we take example that delivery rate, right, delivery rate is the V sub d, delivery rate V sub d, let us say typically say 200 meters per minute. Rotor speed, let us take, let me take 1,20,000. Nowadays, rotors are going even higher than that, but many cases people use 1,20,000 or 1 lakh and all that. Now, what will be, so we know Vd, what will be the value of Np? Np is equal to Nr, this is N sub r, rotational rate of the rotor, Nr plus V sub d divided by pi d, right. So, this is going to be 1,20,000 plus 200 is the delivery rate divided by, let us take a rotor diameter of about 40 mm. So, this also we multiplied by 10 to the power 3 to convert meter into mm. So, this will come to, this will go to 159, I think 159 into 10 to the power 3. So, total it is going to be 1,21,590 RPM. Okay. So, if you calculate Y max from this, that is going to be V sub d, we are taking 200, we multiplied by this 10 to the power 3 to convert to meter to millimeter, divided by 1,21,590. So, this comes to around 1.64 millimeters. Okay. So, few millimeters, that is what is given there. So, it is very, very small, even Y max is very small. So, what will be the effect of that? on the yarn structure. On the yarn structure, right, the fiber is getting delivered continuously from the delivery tube or delivery channel or fiber transport channel, right. So, in the process the material is delivered onto the peel off point, right. Since the gap between the peel off point and the next section, the gap is only few there can be fibers which are placed on the peel off point and in the gap also. Now, what will happen as the yarn is getting rotated, the torque is going to flow and it will introduce twist into the main section of the yarn, and also since fibers are very close, the fibers which are on the gap, which is only few millimeters. So, these fibers will also be dragged on to the rotating arm of the yarn, right. So, these fibers then they will bridge the gap, basically they will be in the gap as well as in the rotating arm, right. So, that is why they are called as the bridging fibers. Now, in order to overcome the resistance of the friction barrier, as the yarn rotates, right, the torque flows in and it has to overcome the friction of the fiber to the rotor surface, right. So, if we give false twist, the navel if it is having a grooves, that will give a false twist over there, it will give a higher torque. So, the torque will make the twist to flow into the periphery also, the fibers, right. So, that is called as a periphery twist extent or the tying in zone. So, if the tying in zone also is going to have the twist, the yarn which is there in the tying in zone, which is already twisted, on top of that the new fiber is going to be delivered, and also the fibers which are delivered onto the gap, that also is very close, since it is a few millimeters. So, these new fibers they will be also integrated into the already twisted yarn. Okay. So, that basically is going to form wrappers. Those who know the structure of the rotor spun yarns, it has a wrapper fiber also. This is the reason, because the Y max is very small, right. So, Y max here it is very small. So, as the fibers are getting deposited onto the gap also, so these fibers do come in contact with the already formed yarn. Okay. So, obviously, these new fibers cannot go into the core of the yarn. So, they can only take the surface, right, and just wrap around that, and this wrapping is going to depend on where exactly the fiber is going to be meeting the yarn arm. Okay. So, accordingly it will have a same twist. If the yarn is S twist, it may have S twist, or if it is coming from the opposite direction, it may form a Z twist also. So, the wrapper fibers can be S or Z twisted when the core is S twisted. So, the direction can change. Okay. Now, this we can see from this high speed photography also, as the yarn here, the peel off point is here, it is taken towards the navel here, right. So, the gap should have been somewhere here, right, but since it is only few and fibers are continuously deposited, if the the twisting torque is not high enough, then you may not even see the gap, very so small. That is why the torque given should be high in some cases, so that the wrappers are going to be avoided little bit. Okay. So, you can see the fibers being picked up from the back of the ring also. So, these are called as the fiber catenaries, and these fiber catenary fibers, if they have to be accommodated in the yarn structure, they will be forming the wrappers, right. So, the wrapper fibers is going to be formed. So, that means we need to have a better understanding about how much gap is there, how much it is increasing, and also we need to have some expression for getting the number of layers, back doubling from this process, right. So, that we can do by simple analysis of how fiber ring is forming. I stop here. Thank you everyone.